this is Hans Kruse, and this video talks about IP addressing. It was produced in conjunction with my course ITS 6250, Information Networks, and it would be helpful if you have some idea of what IPv4 and IPv6 addresses look like, for example, from the reading in that course. In this video, we'll talk about how networks are defined. We'll talk about subnetworks. We'll talk about address hierarchy. We'll talk a little bit about how all that is related to routing. So in a typical network, we're interested in one particular node and how it handles forwarding packets. So this node here, the green one, is about to receive a packet. And because this is the internet, we're using datagram routing, which means that this packet is identified by its destination. In this case, an IPv4 address, 132.235.0.1. This is written in the conventional way. Each digit is a decimal digit and represents 8 bits. Now, since we're all-knowing, we already know that this packet needs to go over here on the right to Ohio University, which has the addresses 132.235.0.0 through 132.235.255.255 assigned to it. Those are the addresses that Ohio University can use. Our node has to figure out whether it should use Route A, Route B, or Route C. Now, actually, if you look carefully, all of them can lead to Ohio University. So there is a routing decision to be made here as well. And addressing and routing are linked in this way, and some others we'll talk about in just a moment. So naively, we could then say, well, why don't we tell this node that 132.235.0.1, the address of this packet, should be, let's say, routed on the most direct way. It looks like the most direct way, going via B. Well, the problem here, of course, is that other packets will arrive with other addresses, so we're going to have to put in an entry that says 132.235.0.2 should also go down Route B, and so for the next one, and so on and so forth. That is not going to work too well. That list is going to be way too long for a node to have to search every time a packet shows up, so that's not what we do. We take advantage of the fact that addresses are grouped. We already know that Ohio University has a list of addresses that are related to each other. So we're not going to do this. We're not going to make a list of all the addresses at this node. Instead, we're going to say that 132.235.anything goes to down path B, and ultimately the other nodes will do the same sort of lookup and get it over to Ohio University. How does the node know that when the packet comes in that 132.235.anything is supposed to be treated together as a network? Well, originally in the internet, that was actually built into the addresses, the address classes. So 132.235 actually was in a range of addresses that all form networks that use the first 2 decimal digits to identify the network, 132.235. That turned out to be not flexible enough, so we don't do that anymore. Instead, we tell the node that the first 16 bits of this address make up a network, and therefore any packet where this first 16 bits match 132, that's 8 bits, 235, another 8 bits. So anything that starts with 132.235 and therefore matches the first 16 bits goes down path B, and then ultimately through the other nodes will make its way to Ohio University. Since the information is no longer carried in the address, is not part of the addressing anymore, we need to get that information to the node. And that's another place where routing plays a role in addressing. We need to get this information about that /16 to the node somehow. Again, that's a subject of routing protocols and network configuration, and a subject of a future video. For now, what we've learned is that networks are identified by specifying the number of bits in an address that groups addresses together, and that information is stored in a node that has to make decisions. Now, we can take the same approach also to create something that are called subnets. For that, let's focus on Ohio University's use of this block of addresses, because clearly we want to, at this node here, have the same advantage of not having to have a list of every address and where in the network it might be found on Ohio University's campus. Instead, we do the same thing we did at the other node. So for example, 132.235.67.0, where the network's defined as the first 24 bits, is the ITS lab in Schoonover Center. 132.235.201.0, also /24, is a different network because it starts with a different set of 24 bits. This happens to be in the Stocker Engineering Center, the Internet Engineering Lab. And by the way, 132.235.0.0/24 is a valid subnet, and it is a subset of the whole network. So in this way, Ohio University can create sub-networks, just the same way that the Internet looks at Ohio University's block of addresses as a network. Each of these smaller blocks are considered sub-networks at Ohio University. The neat thing here is that anywhere else in the Internet, that knowledge is never known. The rest of the Internet still thinks of 132.235.0.0/16 as one network, and that is as it should be. That is how it works. So we've talked about networks. We've talked about subnetworks, which means an entity that has a network, a block of addresses assigned to it, can further subdivide that block. Now let's talk about address hierarchy, and for that, well, we're going to take a little bit simpler network. We'll use still in the green circle over on the right, and this time our node receives an IPv6 network, an IPv6 packet. IPv6 addresses, quick reminder, contain 128 bits. They're written in hexadecimal digits. Each hexadecimal digit represents 4 bits. So each block of 4 digits represents 16 bits. So 2610, the first block, first 16 bits. Now it gets a little tricky. A8 is really 00A8 and represents the next 16 bits. 4831. 301 is 0301. And then the double colon sort of fills in the missing zeros to make up a full 128 bits. So this particular packet wants to go to an IPv6 network at Ohio University. In particular, that network is defined as 2610 A84831.300/56. Okay, quick check here, 56 bits. 2610 is the first 16, 00A8 is the next 16, that's 32. 4831, another 16 bits, so that gets us to 48. So we need 8 more bits, that's the 0 that's not there, and then the 3. So so half of that last written block, 03, is part of the network number, the 00 is not. In fact, University, of course, has many of these networks. There's another one. There's another one. These networks are sub-networks, and they're part of Ohio University's network. So nothing has changed yet. If you look at the routing information, you look at Ohio University's network, and if you look at the sub-networks, while the addresses are longer, nothing has changed. Our node over on the left has a 48-bit network, 2610.00A8.4831. Anything that starts with those 48 bits gets sent to Ohio University. And at Ohio University, we then subdivide that block into smaller subnetworks. So that's all good. Now the problem with address hierarchy comes in when we say, well, here are two more institutions that are served by the same node that Ohio University's traffic comes through, this one here. And so these two networks, these two institutions require networks. And if I just randomly assign networks to these two, then the node, our node in the internet has to keep adding entries for these new networks. But I don't have to do it that way. I can start by assigning a very large network, a very large block of addresses, to the service provider that serves all three, Ohio University and the other two institutions. In our case, that happens to be Ornet, the internet service provider for the state of Ohio. And its network, assigned network, is 2610A8/32. And if you check quickly, yes, all of Ohio University's addresses start with those 32 bits, 2610A8. What Ornet can now do is it can assign networks that are different from Ohio University but start with Ornet's prefix to other institutions. So 2610A8/4832/48 is different from 4831/48. So those are different networks, and each of those institutions would then subnetwork theirs. But they all follow the same prefix that Ornet has. That means our nodes in the internet can now forget about Ohio University and instead route based on Ornet's prefix. That is called hierarchical assignment of addresses. Ohio University and the other two networks are not related. These might be other universities or state agencies. But the service provider that handles all of our traffic is an aggregation point. It is a point in the hierarchy, and it makes it easier and more efficient to route. There are some downsides. If Ohio University wanted a second connection to the internet or change its providers for some reason, some complications would arise again. Those will be a subject of a future video. I hope you have enjoyed this review of how we define networks by choosing the first few bits of an address to be common among all the addresses. The concept of subnetworks, where an entity that's been assigned a network further subdivides it, and the kind of the reverse of that, the hierarchical addressing, where unrelated entities, unrelated networks are assigned out of a larger super network to simplify routing. I hope you have enjoyed the video and will watch others in this series at a future time. Goodbye for now.